Hello everyone. In this video, I want to introduce you to a distribution calculator that can be valuable when you are introducing the ideas of the normal distribution, the binomial distribution, t-distribution, and other common distributions that you might use in an introductory statistics course. A couple of points of interest here for this distribution calculator is this first drop-down menu selects the type of distribution. As you can see, there are lots of distributions that probably wouldn't even be covered in an introductory statistics course, but the usual suspects are here with the normal distribution, the uniform, the chi-square, the F, students' t-distribution, Poisson, and binomial. So each of these distributions has parameters that students can specify within this calculator and then calculate areas and percentiles associated with each of those distributions. Now, to compare and contrast this calculator with what a student would typically encounter in their introductory statistics course, I just want to bring up a standard normal table here that a student would have to master to be able to calculate areas from a normal distribution. This particular table doesn't give a graphical representation of what areas in the table represent, but it does tell the user that the table values represent areas to the left of the z-score. Many of you are probably familiar with interpreting these kinds of tables. Your students that are taking a statistics class for the first time, however, will not be, and this can be a source of confusion for them. This table will not cover every single area associated with every single z-score. They've picked sort of the major players and they've been smart about it here, but this can be a source of confusion because when a student is trying to find an exact probability for a z-value that's not contained in this table, they're not going to be able to do that. They're going to have to find a range or try to do something like linear interpolation. A better way would be to leverage the technology we have of calculating exact probabilities for exact values that we're interested in for that distribution. So if I have from my distribution calculator, the mean and standard deviation specified as 0 and 1 respectively. What we're looking at here is a standard normal distribution, and I can calculate areas that are less than a specified value. The default here is 0. Areas greater than that value, and you can see as the user chooses these different options, there are shaded regions that are shown corresponding to the area that's specified. This reinforces the student's intuition behind what they think they're calculating. In addition to calculating areas from the normal distribution, I can calculate percentiles by specifying that percentile in this probability statement. For example, for the standard normal distribution, if I want to find the 95th percentile, I can put in 0.95, and this red line shows me that this is the percentile that has 95% of the area below it and 5% of the area above it. That value is 1.645. Similarly, I can find confidence intervals from any normal distribution by selecting this confidence interval option and specifying my confidence level. For a 95% confidence interval, that's going to be the traditional negative 1.96 and positive 1.96. Now, this distribution calculator obviously will allow you to do more, calculate areas for more than just the standard normal distribution. So if I have a mean of 45, standard deviation of 6, for a normal distribution, I can calculate the area of being greater than, say, 55 by selecting greater than and 55. That's going to shade this particular area. I can confirm that that's what I actually wanted, and then report that that area is 0.0478. No need to go through the standard normal to get there. Similarly, I can find the 90th percentile from this normal distribution with mean 45 and standard deviation 60 simply by asking for a probability of 0.9 with the quantile option specified. That red line shows me, it can confirm, yes, that's where I think this is going to be 90% of that area below it. That's what I wanted. And that value is 52.689. All right, let's work through a brief example here for the normal distribution. In this example, we're looking at body mass index for men age 60. That's known to be normally distributed with a mean of 29 and a standard deviation of 6. And I want to find the probability that a male age 60 has BMI less than 35. So if your students are trained to draw this normal distribution and shade the area that they're interested in, they would get something that looks like this, where they draw their line at 35 and we're shading all of this area to the left of that. Okay, so this is helpful, and when we plug those values into the distribution calculator, we should see something that matches what we are sort of visualizing for ourselves there. So I'm just going to come to my normal distribution, put in 29, standard deviation of 6, and the area less than 35. That area is 0.8413. Okay, another common distribution that's used in an introductory statistics course is this binomial distribution. And things that characterize the binomial distribution will be the number of trials and the success probability. By default, that's set to 10 trials and a 0.5 success probability. And it shows me that I can calculate areas, quantiles, confidence intervals, etc. For a variety of options, I can calculate the probability of exactly X as a specific number of successes in those n trials, less than X successes, less than or equal to, greater than or equal to, strictly greater than, between, and then areas in the tails. And like we saw with the normal distribution, when I specify these areas, the distribution is going to shade those so I can visually confirm I am calculating what I think I'm calculating. So for example, maybe I have 20 trials and my success probability is 0.6. So now not only am I doing more than just looking at values in a table, I am able to see how they relate to each other and start to appreciate some of the symmetry that exists between probabilities in this binomial distribution. To appreciate what we're doing here, let's take a quick look at a binomial probability distribution table that students will typically encounter when they're first faced with a binomial distribution. This table starts off with the total number of trials, n trials along the far left, and then it keeps track of probabilities that are associated with specific number of successes. So if I had 2 trials, I could have 0, 1, or 2 successes, and depending on what the success probability is along this row, I am given the probability of exactly that number of successes. Now, it doesn't take much imagination to get to a point where this table is limited as to what it can provide. If I wanted a success probability of 0.63 or 0.27, I'm not going to find that in this table. In fact, for the number of trials even, this takes me up to 20, and then it jumps to 25, and then it stops. So that's where this binomial distribution calculator will be really handy. A couple of features for this: when you specify the number of trials and success probability, if you have area and the probability of exactly observing that number of successes, let's take for example 12. This is going to shade the number of successes that you're wanting, and it's going to reinforce that you're getting exactly 12. If users hover over each of these number of successes, they can see the probabilities that are associated with the heights of each of those bars. Additionally, that probability is, if I've specified that probability of 12 here, it's going to show me what that probability is in the lower left. Now, if I want the probability of less than 12, it will calculate that for me as 0.4044. Notice that it shades 11 and below because I want strictly less than 12. Let's look at a quick example of computing probabilities from the binomial distribution using this distribution calculator. In this example, we have a medication for allergies, and we know that it's effective at reducing allergy symptoms in 83% of patients. So our success probability is 0.83. That is not a probability that's going to be given in that binomial table. If the medication is given in 10 patients, here are the probabilities we want to find. The probability it's effective in exactly 7, or the probability it's effective in at least, let's say that it's effective in at least 5. Okay, so to find those probabilities, I'm going to come over here to my binomial distribution calculator. I'm going to put in 10 with a success probability of 0.83. And then I want the area associated with exactly 7 for 7 successes, and that's 0.1600. If I want the probability that this medication is effective in at least 5, so I'm going to say greater than or equal to 5. That's going to shade 5 and above. I can confirm, yes, that's what I wanted. That's 0.9973. Okay, so hopefully this gives you an introduction to this distribution calculator that will be useful as you introduce these different distributions in your statistics class, and really allow students to dig into the concepts and visualizations behind those probability calculations and those quantile calculations. All right, good luck and enjoy.